This is Algebra 3, Unit 7.2, Finding Probabilities under the normal curve. We're still talking about statistics, we're talking about the normal distribution, and we want to be able to use z-scores and find the area underneath the normal curve, which is going to translate into a probability. So guidelines for finding normal probabilities under a curve. First, identify the mean mu and the standard deviation sigma. Second, find the z-score for the standard normal that corresponds to your data value x. We've got this small formula, x minus mu divided by sigma. Step 3, draw a normal curve and shade the area underneath the curve you need to find. There are 3 different possibilities here. The first one is if you want the probability less than x. So you want the shaded region to the left. The second possibility would be that you want the area under the curve to the right, greater than. And then there's a third possibility that you want the shaded region in between 2 values. Here's my mean, some value x1 and some value x2. Find the shaded region between the 2 values. Remember that these shaded regions correspond to area underneath a curve, as well as percentages and probabilities. So, probability that x is less than z, and then this is the probability that x is greater than some standard deviation from the mean, and then the probability that we find some probability between. Finally, our last step will be to either use a z-table or a graphing calculator with the cumulative distribution function. Here's our example. It will make much better sense when we do a real-world example. So no more mean 0, standard deviation 1. Here's some data in which the school SAT scores are normally distributed, keywords, with a mean of 1075 and a standard deviation of 125. I just did step 1 of the process. Identify the mean, identify the standard deviation. So what percentage of students scored greater than 1100? So we are looking for the probability that some score is greater than 1100. Let's translate that into a z-score by writing x minus mu divided by standard deviation, and that's going to be 1100 minus 1075 divided by 125. And that's going to be 0.2. Next, I'm going to draw my normal curve, shaped like a bell, except no mean is 0. In this case, it's 1075. And we want values greater than 1100. We have to find that area right there. And so, let's go to our z-table and look for positive 0.2. And if you look, it's positive, so we're on this side of the paper because we're on the positive side, and we're going to look up 0.020. I've done that already, and I get a value of 0.5793. But remember, the 0.5793 is actually the area to the left of the curve. So this area is 0.5793. And that means to find the probability that we're greater than 1100, that would have to be the complement of being less than 1100, and that's going to be 1 minus 0.5793, which is equal to 0.4207. So now I used the z table, but remember I had to find the complement or opposite probability. The second way I'm going to do this is I'm going to set up the normal CDF, where my lower limit, remember we're trying to find that shaded region to the right. The lower limit is going to be 1100. The upper limit goes to positive infinity. I need to pick a really, really high number, but I can't pick 1,000 here like we did in previous lessons because the mean is above 1,000. So we need a much, much higher number because our mean is no longer 0. It's 1075. And the standard deviation is 125. So let's put this into the calculator, and hopefully we get an answer that's really, really close to 0.4207. Let's pick normal CDF. The lower limit is 1100. The upper limit needs to be a really, really big arbitrary high number. The mean is 1075 with standard deviation 125. Let's hope we did it okay. And it's perfect. It comes exactly out to the same answer, 0.4207. All right, so all of this is going to be part A. But if you look at it, less than 1100 is that opposite probability. So we actually already did part B when we were doing our work. So that should be 1 minus 0.4207, which is that 0.5793 answer. Let's try another. Suppose that in your school, SAT scores are normally distributed with a mean of 1150 and a standard deviation of 130. What percentage of students scored between 1,000 and 1,300? I'm going to set up my probability between 1,000 and 1,300. I'll transfer that into two z-scores, one for the lower All right, that should be a negative z-score because it's below the mean. Which is negative 1.15. This z-score should be greater than 0. It should be positive because it's above the mean, and that's going to come out to a positive 1.15. Now, I am going to draw my picture. Here's my bell curve. The mean is 1150. And we're interested in scores between 1,000 and 1,300. We are trying to find this shaded area. At this point, I would like you to pause the video. You can try either the z-table or the graphing calculator and see if you can solve part A as well as part B. Okay, hopefully you gave it a shot. Now, I am going to use the graphing calculator. But interestingly, when the problem is in between two scores, you do not need an arbitrarily low or arbitrarily high limit because our lower score is given to us, as is our higher score, with a mean of 1150 and a standard deviation of 130. Let's go back to the calculator. Let's press normal CDF, but let's go from 1,000 to 1,300, mean 1150, standard deviation 130. And I get an answer of 0.7514. So 75.14% of the students score between 1,000 and 1,300. Part B. You should have tried that as well. Hopefully you realize that it is the complement because it's the other parts of the bell curve. So those are the complements right there, and that's going to be the probability of between, or rather less than 1,000 and greater than 1,000, greater than 1,300. Is going to be 1 minus 0.7514, and that gives us 0.2486. So 24.8%. There you have it. Please comment on this video in order to earn credit. And then, have a nice day.